dictated by logistic for trailer clearance. You can see here there is a trailer under the module that is carrying the module, and for this purpose we have to allow a certain clearance. Of course, otherwise we did not need this one. And the roof height is dictated by equipment height, piping, and crane clearance. For modules, there is one study that we have to do all the time, is the weight control and center of gravity are important for checking the road capacity. The weight control is for road capacity, and the module stability during transportation. This is why, for instance, you have here a trailer that's very long, because the road was not strong enough to be able to carry a concentrated load. You know, if you have a small area and lots of load, then the road was not able to. Sometimes we have to cross a bridge, for instance, and they cannot go around that bridge, so therefore they have to go by the limitation of the capacity of the bridge. Any questions so far?
I mean,
yes.
I'm wondering, maybe we should mention that in the last 17 years, Parsons has been the only company that really has been specialized in
right.
Doing Arctic work.
Yes.
So we are it, if I may say.
Yeah, we really are the most experienced. Actually, when we were kind of joint venture with Fluor on the Sakhalin project, they came after us just to learn how to make modules, and and they did pretty well, and now they are doing modules on their own, but smaller modules, you know, like these modules are really 1,500 to 2,500 ton modules. So far they have never nobody has done those large modules like 5,600.
So, I mean, during the trip, who's doing the study of the load on the bridges of the road and the routing? Is that our or someone else?
No, this is logistics. This is the job of logistics, basically, to figure out how to transport a module. You see, our business is a structural business is to build this in an assembly site, and then from there on, it's handed to logistics. Logistics decide how to transport it. I will briefly describe a little bit the most important items of transportation, but whoever decides, for instance, the length of this RTV is decided by logistics based on maybe information from civil and the routing and how you can reach the site from the loading dock, because you know, Michael will explain this. Basically, you have to go from the assembly site to a dock area, a port, and that's a barge. And then from the port to the site, you have RTV. Now, of course, sometimes even the assembly site is far from the loading dock. Then also you have to use RTV plus barge plus RTV. So this will be addressed by Mike. Go ahead.
August 15th, we'll be giving a presentation on SEALs under the Arctic design criteria.
Yes.
Mike McKenna is the manager of logistics, and together with Tom Butler. So any logistic
yes.
question, we have to go to Mike. Routing and transportation.
Yeah, and in order to know what are the conditions of the site, all this, definitely civil is part of the work, and in order to know what happens when the barge and the modules in the sea, Mike also hires naval architect to help, you know, decide on the routing and what are the waves that can happen on that route.
I think the good thing to note is that it doesn't all come together at the end. It's a process all from the very beginning.
Yes.
To study and work together, what you guys deliver, what you guys move. Sometimes it can be delayed if you design a whole module and here it is, you deliver it, maybe too wide.
Oh yeah, oh yes, yes, absolutely, yes.
It's a process being very.
That's very true, yes. Well, of course, we all work together, in the design phase. All the disciplines are working together to put it together, And everybody has constraints and has their own discipline. They need certain things, and all this effort is done. That's why we have, normally we have conceptual, then we have preliminary design, we call it define phase, and then we have the execute. So, as you said, it does not happen all of a sudden. Nobody makes the decision alone. It's all a group decision. Okay, I'm going to show you some pictures of sea-lift modules during construction, because this will really explain more what are the components of a module. You can see here, for instance, how it is put together. You have columns here, we call them stop columns. You have plate girders. You have equipment. Now, in this case, they decided to put the equipment before the superstructure, is on. So sometimes they put the equipment first, and then they start building the columns. So you can see the different components until it reaches the stage. This is another picture also. Here they started putting the architectural. We don't have an architect here, but I will briefly talk about architecture. Those are the siding for one wall already. They put it in place. So this is like maybe 3/4 complete, because this module will have lots of equipment is already there. Maybe not final setting, but they are in their position, for maybe they tighten the bolts at the last minute, but they are there. Because the access is very important. You cannot always access later on. Now, this is the modules that we are designing for GPP. This is one module that's the 602, the utility module. This is about 3,000 tons module. Okay, what are the components of the sea-lift module? We have the substructure, that's a rigid base for supporting the equipment that we will show more about it. We'll talk more about it later. And then we have in the structural language, you call it substructure for this base. This is the base. That's a substructure. And then we have a superstructure, which is everything above the base. We call it superstructure. It consists of columns, like these columns. Roof, of course, you have a roof here, A cooler platform, that's a platform that is independent of the roof, normally. And then we have intermediate platforms. For instance, here, there is an intermediate platform inside the module. And then we have integrated pipe racks, because also inside the module, we have a part of the module here between these two columns is a pipe rack. And normally, when we have several modules next to each other, this pipe rack continues, and then later on it will merge with the main pipe rack, which is outside. Normally the main pipe rack is exposed in the North Slope construction. It's outside. But this is all integrated into a module. And then we have cranes and lifting equipment, and we have architectural 2-inch insulated siding for weather protection. And then we have equipment, piping, electrical instrumentation, all this. Now, definitely the cost of this is about maybe 80% or 85% of the rest. But we put it in one item here, but it does not reflect really the importance. This is very important, the equipment and all this. But here we are, because we are emphasizing on structure. Okay, so here I will explain a little bit each component, the rigid base component. Typically we use 5 feet girders, about that high, and these girders include, many times they are used, and they include electrical openings. Whoever is involved in electrical and GPP design, they will see that we will use the base because it's high, and it does not hinder the structural function really. That we can use it for structure, and we can use it also to locate all those cables and the cable trays. And we use it also for drainage, pipes. Drainage is within this 5 feet. We have done on that project, Sakhalin, for instance, 4 feet. And 4 feet structurally was good enough, but then we regretted because 4 feet, we could not locate the electrical cables and drainage. 5 feet is not much more expensive than 4 feet, really, but then it has a function, a much better function. So,
lifting lugs goes into the base?
there are no lifting lugs here. We do not lift this. This is all transported by RTV. You see? Okay. Now, locally, maybe sometimes what they do, they can prefabricate a piece, you know, like, or a piece of base, and then lift it and put it and assemble it with the rest. But that will be like kind of temporary lifting.
So
No.
how do you select the
RTV?
Under that, you just
Yeah.
like,
Yeah.
the column there.
Okay. Here I'm going to explain this. First of all, let me continue. Here it will come. These plate girders are transverse plate girders and longitudinal plate girders. So they form a grid, really, and that's very rigid grid on which we can put an equipment as heavy as this. And even we can test it, you know, water test. So imagine this one full of water. That's very heavy, right? And still, this base can take the load. That's covered with checker plate. We cover this with checker plate, fully welded for waterproofing and gas proofing. And because we do not want any gas to be entrapped in the base, because that will create explosions, or maybe somebody, if he goes in, he can suffocate. But it's also explosions is very dangerous. So basically we will do this completely waterproof and gas-proof also. Then we have 2 rows of stop columns. You see, these are the stop columns here and here. There are 2 rows, 1, 2, 3, 4, 5, 6, 8 in this side, and 8 in this side. And between the two, there is empty space. Those are all temporary from construction. And this is where, between this and this, that's where the RTV is going to go in, because we have enough height. We have allow 8 feet height clearance from here to here for the RTV or trailer to go in. The trailer goes up and down, by the way, so when we want to go under this, we have to lower it and then go under it, and then when we want to transport the module, Mike McKenna will push a button and raise the RTV, and then the module is carried. It's all hydraulic. Yeah, it's a push a button really. But you have to know, you have to balance it. Remember when we said determination of center of gravity, this is very important, because the RTV is all like hydraulic. We will explain a little bit more. Hydraulically connected, so it cannot take unbalance. You have to know exactly where is the center of your module and adjust the RTV to that exact center. The center of the RTV, the center of the module have to match, and then at that time you can raise it. And now, if it doesn't match, then automatically it will tilt, and then Mike will know and move it, and that he will explain in his presentation more than this. But here, suffice to say, that this is how we transport it, and that's why we provide the tool, the means for logistics to be able to do that thing. And this is determined by logistics, as I mentioned earlier. 8 feet is what is convenient for logistics. We can do it 5, 6 for us. It doesn't make much difference really. But now, another feature of the base is that it has to be designed early, because they want, normally the project wants this base to be there very early so that they can start putting equipment on it. And if the base is late, then the whole project will be late. And that's why most of the time the base is kind of designed fast, even with preliminary values from equipment, and with our experience, we kind of little bit make it on the safe side, and just issue for construction, and then later on we will adjust it for minor loading that are between the plate girders. But the plate girders are very important to be purchased and fabricated and ready for equipment installation. Any question? Okay, now superstructure components. The superstructure components consist of moment connection transverse frames. From here to here, I can show you. From here to here is basically one frame, and these are the side frames. And then we have longitudinal braced frames. Those are the longitudinal, from here to here longitudinal, and those are braced. Not like the transverse frames that are moment connected, because we cannot put any bracing in the transverse direction. Most of the time, piping and equipment, and they want to put their stuff. So they ask us, okay, give us clearance. It's like this room. If you start putting columns here and stuff like that and braces, you cannot put people. So same longitudinal. Now the roof is normally spans over the whole width. It spans from here to here, the roof. And the brace, and it's braced here to create a diaphragm action, such that when we have a wind or seismic or acceleration due to barge, some of these loads is transferred to the side frames that are braced. Because the moment connection frame cannot take too much really. It can take, but it will deflect a lot in order to take. But these, because of the bracing, they restrict the deflection. That's why structural people like to put bracing, because you restrict the deflection. It's not necessarily the strength. The strength you can take, but imagine a frame that moves at 2 feet. It's not going to fall, but it's too much, and therefore you like to have braces to limit it to a few inches, 1 or 2 inches, something like that. That's the order of magnitude. And then we have intermediate columns for pipe rack support. For instance, because we have here between these two pipe racks, we try to put as much as possible intermediate columns if we are allowed. And then we have a cooler platform. For instance, here there is a cooler. Here there is no cooler. Here there is a cooler, so we have to build a platform for the coolers to sit on. Here there is no cooler, but we still have a platform to put the ducting. Those are all HVAC ducting. And HVAC is very important aeration in modules because of the aeration purpose of the process knows why, but we do provide supports for this HVAC, and some of this support is here. Cooler platform for top. And now next, components also, the other components of the module is cranes and monorail. Those are important items. For instance, you see this module, we have a span from here to here, but in some cases we were able to brace part of the frame. And those cranes if, for instance, you have an equipment here, heavy equipment, and or a compressor or equipment that needs maintenance, then the cranes will be handy because you can remove, maybe not the whole piece, but items like the rotor and some parts of the equipment, they're already pretty heavy. They would be between 10 to 20 tons capacity. So we need it. And also, if we have pumps and valves, then monorails are provided. Monorails are simple beams with a mechanical, with hoist, mechanical people. If there is anybody here, they would know what. But monorails basically are simple to design, and we just put them and support them with just transverse beams. Okay, now architectural components. You see, architects are mostly in petrochemical, very rarely used in refineries, except for control rooms maybe. But for modules, they are an important contribution for modules, because they have to cover the modules. Typically, 2 inches insulated panels are provided for weather protection. So we use the same panel for the siding, for the roof, and for the soffit. Even the soffit below has to be covered with insulation. So it's like a box, closed box. Now, for instance, there is one phenomenon that process people would know about, is if you have a steel partially exposed, for like this one, for instance, this steel is inside the module, this steel outside, partially exposed, then there is a condensation phenomena that happens here, then because it's cold, part of this cold goes inside, and it condensates the air, the humidity in the air. So we want to avoid this. So therefore, we would put the same siding for a certain length of maybe 2 to 3 feet on this. And that's a detail that is important for the architect, because they don't have all the time space to put all these sidings, around this. So we have to work with them to provide. That's part of the design, really, is to make the design constructible and at the same time possible for other disciplines to put, because the module is very congested. We cannot just put steel everywhere. We have to leave space for all the other equipment, even including siding. And finally, we have the equipments that are major part. As I said, that's probably 80% of the cost. And they are a major part of that's why we have a module in the first place, is to locate equipment and make this equipment function and do the work for the purpose. Equipment include turbines and compressors and the generators, if you want, waste heat recovery units, stacks. Those are like, for instance, here we have 2 stacks, vertical, horizontal vessels. This is a vertical vessel here. This is a horizontal vessel. Even you don't see it very well, I'm sorry. Exchanger, these are exchangers here. Coolers, as you see, electrical instrumentation, and mostly piping. Piping is all over the place, connecting all this equipment. And then module fabrication and transportation. Very briefly, I'll say something about this. Module fabrication and transportation, we will cover steel material, fabrication, assembly, land transportation, sea transportation, and foundation setting. So steel material, for the North Slope, we have to have, because of the harsh weather, we have to have a steel material that's not the same as we use here in California. It has to be ductile, not brittle, more so than other places. Always in seismic areas, you need to have ductile steel. But for a different purpose, there is no seismicity, by the way, in the North Slope. It's not. It's very low seismic area. So it's not a problem from the seismic point of view, but it's a problem from the cold weather point of view. The chemical composition of the steel is very important for cold weather. And they test it with some test called Sharpie test, determines degree of ductility, low temperature from -30 or minus 50. Minus 50 is the most stringent. Exposed steel require more stringent requirement at testing that cover steel, of course. Once this steel is covered, then it's not as brittle, or it's not exposed to this phenomena as much. Thicker members are more prone to cracking than thinner members. Even though I have seen even 1/4 inch plate, checker plate, it cracked. It reached the north slope, and all of a sudden the module, the plate cracks from the beginning to the end in several places. And the reason at that time was the chemical composition was, at that time they didn't find what we were specifying. They replaced it with Japanese steel that does not have the same chemical composition as the steel that we specified. And sure enough, it cracked, and the fabricator was responsible about it, because he took responsibility of exchanging the steel. Now, fabrication, structural member often fabricated in separate shop and transport to assembly site. Sometimes you have a shop that can fabricate and assemble at the same location. Similar like in Korea, Hyundai, they do that. They fabricate, they have a huge space. They fabricate and assemble on the same location. But most of the time in the United States, it doesn't happen like this. Sometimes we fabricate in Sioux City and we assemble in Louisiana, for instance. So we have to fabricate these separate shops, and each transverse plate girder separately like this, and the stop columns are fabricated from plate elements. Maybe this is more interesting for structural people, but not as much interesting for other disciplines. But I just mentioned it here, that it comes fabricated into elements. Most important is that this piece is one piece. And then this piece all the longitudinal are several pieces. And of course the columns are separately. And then we go to the assembly. In the assembly, all the plate girders, transverse and longitudinal, are all welded together, fully welded into a very rigid base. And then the stop columns here are also welded to the base of the, to the bottom of the base. And the superstructural columns are also welded to the top of the base. Transversal beam are welded, like transversal beam is like this, from column to column. This is a transversal beam. Is also welded to the columns, and all the rest is normally bolted. All the rest is bolted. Okay, land transportation. As I said, we will address the land transportation from the structural effect. Mike will cover how to transport it and what determines, what determines the length. For instance, for land transportation, this length of the RTV is determined by the conditions of the road and or the bridges that you have to cross and stuff like that. So now this is our module from here to here. Okay? Now, in order to be able to put this and transport it on an RTV, by the way, an RTV is like a continuous beam. It's very rigid. The RTV itself is like maybe 4 to 5 feet high beams also. It's very rigid. They are all one piece. And they are sitting on tires, and the reaction from the tires is hydraulically connected, so therefore it gives uniform pressure, uniform reaction. So the reaction is uniform, and the module is sitting on a shorter length, so you can see that it will create this phenomena, and this deflection from here to here is what we are concerned. This deflection from here to here, it's the deflection of the RTV. We cannot tolerate, or logistics cannot tolerate more than, say, 8 inches, depending on which trailer they use. And therefore, in our analysis, we have to determine how much is the deflection from this point to this point, and in order to reduce it, we build this extra steel here so that we push back the RTV, into horizontal position. Any question on this? I think it is intuitive that you can see that phenomena happening. But you see, the cost of this steel is, now you can ask, why don't we make a module that's as long as the RTV, let's say? Because of the operations, it will be very costly, the operation, and the air condition and all this. So we want to use as small module as possible for operation, for walking around equipment, maintenance, and all this.